15 astronauts have just landed on Mars. They are not visiting for a few weeks. They are relieving the existing crew and beginning 500 Martian sols of continuous surface operations. Outside, the environment is hostile. Resupply is distant. Every kilogram launched from Earth is expensive, and food is more than stored calories. It is nutrition, crew health, morale, water, power, and mission resilience. The habitat structure is already here. The question is, how do we feed 15 people every day for 500 sols without depending on Earth for most of their food? Our answer is MARSHAB-ONE, a modular, autonomous, regenerative food habitat. MARSHAB-ONE treats food not as an isolated farm, but as part of the Mars habitat. The design point is a 1,200 square meter, two-level pressurized habitat, supporting 15 crew for the entire 500 sol surface mission. Grow the majority on Mars. Bring only what makes sense from Earth. Recover every practical resource along the way. About 65% of crew calories are produced in situ, and 35% are Earth-provisioned, under the challenge's 50% limit. The farm is pre-deployed 132 sols before crew arrival, so biological production is stable before the first meal. The concept of operations begins with a few controlled inputs: water makeup, electrical power, seeds and starter cultures, nutrient salts, carbon dioxide, and selected Earth-provisioned ingredients. These enter hydroponics, aeroponics, spirulina cultivation, mycoprotein fermentation, and mushroom production. Harvested material moves through inspection, sanitation, processing, and storage. The galley converts production into the 14-sol rotating menu. Water, nutrients, biomass, carbon dioxide, and useful heat return to the habitat loops. MARSHAB-ONE is not a farm beside a habitat. It is a food resource ecosystem inside the habitat. Inputs go to production, then harvest, storage, the galley, and the crew. At the center of the architecture is 618.7 square meters of active food production. About 518.7 square meters supports crops, plus 35 square meters of spirulina, 35 of mycoprotein, and 30 of oyster mushrooms. 17 crop species and 3 bioreactive pathways provide carbohydrates, protein, vegetables, micronutrients, flavor, and fresh food. Vertical cultivation uses the two-level habitat instead of consuming only floor area. Cultivation, processing, storage, galley, and crew spaces are separated so material moves in a controlled path from production to the plate. South is processing and galley. East is life support and AI. West is crew. North is the farm. On Mars, producing food is only useful if the resource demand is sustainable. Crops transpire about 1,934 liters per sol, but about 1,895 liters return as condensate. Net food system makeup water is only about 43.9 liters per sol. The 15-person crew produces about 16.2 kilograms of carbon dioxide per sol. Crops consume that carbon dioxide and return about 15.3 kilograms of oxygen. Inedible biomass, about 63.5 kilograms per sol, can support mushroom substrate and nutrient recovery rather than being treated only as waste. The objective is not perfect closure. It is to reduce what must be brought from Earth. Water, air, and biomass are treated as one loop, not 3 separate problems. That is how a food system stays viable for 500 sols. The nominal food system load is about 203.4 kilowatts. Lighting, pumps, climate, processing, refrigeration, automation, and bioreactors. Primary power is solar, supported by about 4 megawatt-hours of battery storage. But food production cannot depend on uninterrupted sunlight. In a major power loss event, the system enters a 73.6 kilowatt safe mode, keeping biology, environment, monitoring, and stored food alive. Backup is about 80 kilowatts of fission-class power, 2 40-kilowatt class units. The system is designed to degrade gracefully. Critical loads stay on. Lighting and processing that are not critical can wait. Automation does not remove humans from the system. It protects their time. MARSHAB-ONE assigns 2 dedicated specialists, a food systems engineer for production, bioreactors, processing, and maintenance, and a nutrition and meal preparation specialist for the menu, food safety, and galley. 2 rostered crew members give about 1 hour each per soul for service and clean down. Specialist food system labor is about 16.9 crew hours per soul. Food safety uses zoning, sanitation, monitoring, and inspection. The commander and medical officer retain authority for safety-critical decisions. Automated crop tending keeps agriculture from becoming the dominant crew activity. Behind the physical system is the digital mission platform. The software connects food system assumptions, mission configuration, resource budgets, crop production, menu, nutrition, crew workload, and contingency analysis in one environment. The crew can examine Mars versus Earth calories, nutrition, crops, water, atmosphere, power, and status. Change the crew population, production capacity, or available power, and the model recalculates. MARSHAB-ONE is not limited to one fixed 15-person scenario. It can become a planning tool for differently sized crews and future surface missions, estimating food and resource needs before those resources are launched. The digital twin is the connecting layer between design, operations, and the meal plan. Overview: Mars versus Earth, crops and menu, water and ECLSS, and crew status are one model, not 5 spreadsheets. Mars will not operate according to the nominal plan. So the software asks a more important question: what happens when something goes wrong? Operators can evaluate changes in crew size, food system power, EVA demand, production capacity, water, or a specific production outage. The mission model recomputes the consequences. That lets the crew see a food, power, water, or labor problem before it spreads, and then adapt production, inventory, operating mode, or the menu. The assistant answers from the calculated dataset. MARSHAB-ONE moves from monitoring what happened to anticipating what happens next. Detect, simulate, predict, adapt, and recover. Every engineering number has to become food on a plate. MARSHAB-ONE uses a 14-soul rotating meal plan with 5 eating periods each soul. Breakfast at 0630, snack at 1000, lunch at 1230, a second snack at 1530, and dinner at 1900. The menu contains 27 unique meals, 21 mains, and 6 rotating snacks, plus contingency items. Breakfast might be potato rosti with spirulina scramble or sweet potato porridge with strawberry. Lunch can be a mycoprotein wrap, sweet potato and peanut stew, gnocchi, or a noodle bowl. Dinner includes roast potato with mycoprotein steak, shepherd's pie, wheat pasta, and stir-fry. On Souls 7 and 14, the crew closes the week at the communal harvest table. That is intentional. Food supports physiology, routine, culture, and social cohesion during a 500-soul mission, not calories alone. Recognizable dishes: rosti, stew, pasta, shepherd's pie. Keep the table familiar so far from Earth. The menu is tied directly to mission nutrition and production. The target is about 3,035 kilocalories per crewmember per soul, with protein protected. Protein comes from mycoprotein, spirulina, beans, soybean, nuts, wheat, and selected earth ingredients. Fresh crops provide vitamins, minerals, fiber, texture, color, and variety. Meals are assembled from components, so portions and excluded ingredients can be adjusted at service. Most importantly, the architecture closes at about 65% Mars calories and 35% Earth. Crew allergen and preference profiles stay in the galley system. MARSHAB-ONE also assumes that fresh production will sometimes be disrupted. A 21-soul contingency reserve is held for all 15 crew members. Electrolyte mixes, EVA nutrition, preserved harvest, and morale foods serve defined triggers. Supplemental foods stay inside the meal rules. Production surplus can be preserved for later souls. 500 souls later, success is not only that 15 astronauts had enough calories. Success is that their food system became part of the habitat. Water returned. Waste became resource. Meals were shared at one table. Food on Mars cannot simply be shipped from Earth. It has to become part of Mars.